Hello, my name is Luke Gamage, and this is my presentation for CS4306 Algorithm Analysis. Today, I will be presenting and analyzing the algorithm called cubical marching squares. So, what is cubical marching squares, otherwise known as CMS? Well, CMS is a meshing algorithm for 3D graphics where the input is a set of volumetric data and the output is a polygonal mesh representation. Now, for a majority of you, that sentence probably did not make much sense, so I will try to elaborate further on what I mean. Well, in 3D graphics, 3D objects can be represented to a computer in a bunch of different ways, but the two ways of concern for this algorithm are through polygonal meshes and volumetric data. Polygonal meshes are the simpler of the two, and it is the representation of an object through a collection of interconnected triangles. This is the method computers are best at and is used in most modern applications of 3D graphics, such as video games, CGI, etc. Volumetric data is a little more complicated, and it is a volume of information about an object that can come in many forms, such as point clouds, scalar distance fields, Hermite data, etc. This form of object representation is used extensively in the medical field with medical scans, as well as their applications of it with AR. With this information in mind, cubical marching squares, or CMS, is essentially a conversion from volumetric data representation to a polygonal mesh representation of an object. To fully understand this algorithm, a brief walk through history regarding this topic is necessary and to understand why this algorithm was created. So, this topic of surface extraction from volumetric data started back in the late 80s with the invention of the marching cubes algorithm by Lorenzen and Klein. This algorithm is an impressively efficient and straightforward algorithm for creating a mesh from a set of volumetric data. The basic outline of the algorithm is to split the volumetric data into a grid of voxels, or cubes, and apply the algorithm on each cube to then create a whole mesh. Hence the name marching cubes. One aspect that made marching cubes so efficient is its ability to process the cubes independently from each other, meaning this algorithm can be run in parallel on a piece of hardware like the GPU, which significantly decreases the computational time. Now, it is important to know the fundamentals of marching cubes because pretty much all algorithms on this topic to come after use marching cubes as a base to improve upon. So while marching cubes is an impressive algorithm, it is not without its problems. The big issues marching cubes has are its topological inconsistencies, the inability to maintain sharp features in an object like corners, and its inability to be applied to an adaptive grid of cubes to reduce the complexity of the outputted mesh. Pretty much all algorithms come after try to fix one or more of these issues. So after marching cubes came extended marching cubes, which fixes the sharp features issues but loses the intercell independency, the ability to run the program in parallel. After that, we have the dual contouring method, which maintains sharp features and can be used on an adaptive grid, but again suffers from intercell dependency. After that comes the topology consistent marching cubes, which fixes only the topological inconsistencies while still maintaining the intercell independency. Which then that leaves us with the cubical marching squares, which It's proposed to offer solutions to all of the problems of marching cubes while still maintaining the intercell dependency, allowing parallel computations. The basic premise of cubical marching squares is, instead of working in the complex 3D environment to solve one problem, we want to simplify that to a bunch of more straightforward 2D problems, which can then be combined to solve the 3D problem. So, instead of working with one cube, CMS unfolds that cube into its 6 faces and runs an algorithm on those 6 faces, and then refolds them back into a cube to generate the mesh. So the algorithm takes in a set of volumetric data, and the first step is to create an adaptive grid, most likely an octree, from that data. One thing to note is that depending on the needs of the output, this step can be skipped in favor of using a uniform grid, especially if the output mesh's complexity is not a concern. The next step is to unfold each leaf cell of that adaptive or uniform grid and generate the segments on all 6 faces of the surface passing through those faces. During this step, the sharp features and topological inconsistencies of each face can be accounted for. After that step is complete, the last step of the algorithm is to extract the surface from the generated segments of each face. This is the step in the process where the cube is then refolded back together, forming the 3D mesh. Each face is traversed, tracing the segments generated, where the next face visited is the one where the end of the current segment connects to, until a loop is formed, creating what's called a component. Using these components, further sharp features and topological inconsistencies can be accounted for. At the end, these components are then triangulated, forming the polygonal mesh. So, cubical marching squares and other similar surface extraction algorithms have a lot of applications in a wide variety of fields. As mentioned previously, the medical field uses a lot of volumetric data, especially with their MRI scans, and CMS can be used to help visualize that data as a 3D object. You can actually see a picture in the bottom right there of visualizing an MRI scan. This algorithm can also be used to do point cloud reconstruction and help in 3D modeling programs to do certain operations, as well as retopologizing a mesh. Lastly, the application that is probably most known and the one I am most interested in is the usage of these types of algorithms for procedural generation in video games. Now you can see in the top right there, that is a picture of a game called No Man's Sky. So games like No Man's Sky, Astroneer, and 7 Days to Die all use some variation of the marching cubes algorithm. Even games like Minecraft and Terraria use the same concept of converting volumetric data to a 3D, or in Terraria's case 2D, object or terrain. With the applications of this algorithm discussed, it is time to analyze how it performs and its efficiency. CMS is, or cubical marching squares, is proposed to run comparatively to the original marching cubes algorithm, which ran for each cube of the inputted volumetric data, making it run in O to the n time, where n is the total number of cubes. For CMS, disregarding the adaptive grid creation, as that requires a whole separate algorithm to accomplish, the generate segments function will run n times 6 times, as each cube has 6 faces. The same is true of the extract surface algorithm, extract surface function, resulting in a total worst case of O to the n times 6 plus n times 6, which of course is simplified down to just O to the n, where n, again, is the total number of cubes. From this, we can see that their times are comparable, of course, with CMS being slower in reality as it is a more complex algorithm that accounts for more details. When choosing which algorithm is best for a specific need, it is important to analyze these differences. And in my case, I think CMS will best fit my needs for a future project I plan on doing. In conclusion, typical marching squares looks to be a promising and robust surface extraction algorithm. The algorithm is efficient with the ability, of course, to run in parallel, allowing for the real-time usage of this algorithm for applications like real-time generation and manipulation of terrain in a video game, like is used in No Man's Sky and games like it. But all in all, researching and analyzing this algorithm helps to gain a better understanding of the topic, and learning about the predecessors especially and comparing them helps to make an informed decision about which algorithm would work best for your needs. So just like creating your own algorithms, the ability to analyze existing algorithms and using that analysis to apply those algorithms to your needs is a crucial skill for any aspiring programmer should have. Thank you for listening to my presentation. If you wish to further learn about this algorithm, please feel free to use the references of this slide.